Okay, please subscribe my channel and watch online, and don't download my lectures. In this lecture I want to prove a theorem about the finite difference, in fact about the divided difference coefficient in the polynomial, in the Newton polynomial. Let me start with the theorem. Let f be a function in Cn of a and b. It means that f and all the derivative of f up to order n are belong to continuous functions over the interval a and b. Then for distinct nodal points like x0, x1 to xn in the interval a and b, we have, okay, now let me write this one. F of x0, x1 to xn is equal to integral from 0 to 1 d of t1, integral 0 to t1 d of t2, and it continues to tn minus 1, the derivative of f of order n times tn xn minus 1 plus t1 x1 minus x0 plus x0 derivative d of tn. Okay, this is the formula. I want to prove this formula. The proof is not too hard, and it can be done by induction over n. So I can write by induction over n. Okay? First, let n be equal to 1. I mean, we have f of x0 and x1. So let me write it here. Let n equal to 1. So we shall to prove f of x0 and x1 is equal to integral. Here you can look, it will go up to t here 0 to tn minus 1, so it will be from 0 to 1. Okay, and here should f prime of n will appear, so it will be f prime of here tn is t1 times x1 minus x0 plus x0, okay, and d of t1. I should prove this one. We should prove. Now, let me start and I try to prove this one. I say use this change of variable. Put xi equal to t1 times x1 minus x0 plus x0. Okay? In this case, d of xi will be d of t1 1 times x1 minus x0, okay, and we can get d of t1 equal to d of c over x1 minus x0. This is the first thing. The other one, we have to change the bounds of the integral. If t1 be equal to 0, so c should be equal to, from here, x0. And if t1 be equal to 1, then c should be equal to 1, x1 minus x0 plus x0. So it should be x1. Okay? So I can compute integral from 0 to 1 f prime times t1 x1 minus x0 plus x0 d of t1. By this change of variable, I can write integral from at 0 it will be c will be x0 to x1, and here f prime of c times dt1, it should be dc over x1 minus x0, and it will be 1 over x1 minus x0. Okay, integral from x0 to x1 f prime of c dc. And this integral, I know it will be f of x1 minus x0, f of x0. So it will be f of x1 minus f of x0 over x1 minus x0, and we know that this is exactly equal to f of x1 and x0. So for n equal to 1, everything is okay, and I put a check mark here. Now, let for n, okay, we have this equality. Okay, let me mark it as star. This is the in fact assumption of the induction. Okay, so let it will be true. Let me do something more. Let me, for n minus 1, let me put n minus 1 and let me rewrite it. We have f of x0 x1 to xn minus 1 will be equal to 0 to 1 d of t1, 0 to t1 d of t2, and continue 0 to tn minus 2 f derivative of order n minus 1 tn minus 1 times xn minus 1 minus xn minus 2, and it continue until t1 times x1 minus x0 plus x0 dtn minus 1. Okay, let this is true. We have to prove for n. Okay, we have to prove for n star is correct and start is okay. Now let me do a change of variable. Let c be equal to tn times xn minus 1, okay, plus and t1 times x1 minus x0 plus x0. So in this case, d of Tn is equal to d of xi. This one should be T1, I guess. Here, something wrong. It should be T1, yeah. D of xi over xn minus 1. Okay, now keep it. And consider Tn equal to 0. If Tn will be equal to 0, so xi is equal to Tn minus 1 times xn minus 1 minus xn minus 2 plus, and it continue until t, it should be T1. Why I write again wrong? T1 times T1 times x1 minus x0 plus x0. Okay, and if Tn be equal to Tn minus 1, here I mean in the integral, here, Tn minus 1. So I will get xi will be Tn minus 1. If I put Tn minus 1 times xn minus 1 plus Tn minus 2 times xn minus 2 minus xn minus 3, and it continue until T1 times x1 minus x0 plus x0. Okay, so in the star here, so in a star here, this integral, if I consider this integral, and I call this integral as I. Okay, so I can write this integral I equal to, so I, which was equal integral from 0 to Tn minus 1, derivative of order n of f at Tn xn minus 1 and plus T1 times x1 minus x0 plus x0, yeah, dTn. Okay, this will be, I put instead of Tn from here, dTn from here, and I do the change of variable and I change the bounds to get equal to integral from xi 0, and let me do some change here. This will be xi 0 and this will be xi 1. Integral from xi 0 to xi 1, derivative of order n at xi d of xi over xn minus 1, and it will be fn minus 1 at xi1 minus fn minus 1 at xi0 over xn minus 1. Okay? Now, take integral from both sides of this equality. Okay? Let me take integral. In fact, the integral, but not the regular integral. Let me write a little more. Now, take integral 0 to 1 dt1, 0 to t1 dt2, 0 to tn minus 2 fn minus 1 d t minus n minus 1 from both sides of, let me call it 2 star. Okay, I mean from this and this. I have to take this integral, okay, of 2 star. What we get? We get here from the left hand side, I get integral 0 to 1 dt1, integral 0 to t1 dt2, 0 to tn minus 1 dtn minus 1, and finally 0 to tn minus 1, 0 to tn minus 1, okay, and the continuation fn times here tn xn minus xn minus 1, tn times xn minus 1, and it continue until t1 times x1 minus x0 plus x0, okay, dtn. This is the left hand side, which is exactly the star. Yeah, remember that? It will be exactly star, okay, and it will be equal to, take integral from here, put 1 over xn minus 1 out of integral 0 to 1 dt1, 0 to t1 d2, 0 to tn minus 1 dtn minus 1, and here tn minus 1, tn minus, it should be tn minus 2, and also this should be tn minus 2. Yeah, let me remove it again, tn minus 2, okay. This one, it will be fn minus 1 at x1, okay, dtn minus 1, right? Yeah, right. And let me put a bracket here and split this into 2 integral, 0 to 1 dt1, 0 to t1 dt2, and continue 0 to tn minus 2 fn minus 1 c2 dtn minus 2, okay, and let me close the integral. Finally, let me do it a little simple. It will be equal 1 over xn minus 1 times 1 plus 2. Okay, let me call it this one 1, and let me call it 2. Okay, now I have to compute 1 and 2. Let me do it. For 1 is equal to integral from 0 to 1 dt1, integral from 0 to t1 dt2, and integral from 0 to Tn minus 2, Tn minus 2. Yeah, am I right here? Yes, Tn minus 2. Fn minus 1, okay? And let me put instead of xc1 from here, yeah? So I can get Tn minus 1 times xn minus 1 plus Tn minus 2 times xn minus 2 minus xn minus 3, and it continue until T1 times x1 minus x0 plus x0 dTn minus 1. And by the assumption of induction, okay, this is equal to f of x0 to xn minus 2 and xn. This is true by the assumption of induction. And in the same way, you can compute 2, okay, to form of 0 to 1 dt1 and 0 to Tn minus 2 Fn minus 1 something is equal to f of x0 to xn and xn minus 1. Okay, this is by the assumption of induction is true. Now, if you put these two item here instead of 1 and 2, so you can get star equal to 1 over xn minus x n minus 1 times f of in fact x0 to xn minus 2 and xn minus f of x0 to xn minus 2 and xn minus 1, okay? And this is nothing except f of x0 to xn, and these complete the proofs, okay? And in fact everything is okay, and I can put the famous square here, and the proof is complete and everything is okay. Now, this is in fact an very important equality in Newton interpolating formula and in fact in divided difference. We can use this formula in lots of problem and lots of other theorems. You can find lots of in fact use of this theorem in the books. So let me finish this lecture here and continue in the next lecture with Hermite interpolation. Please subscribe my channel and do not download my lectures and watch online. Thank you.